Today we want to continue the plane. The volume is cross-section area multiplied by height. And we're going to do that with a volume of a solid of revolution. So this is just a small variation on the theme that we've already had. So if you recall, we had a couple problems where we had to figure out what the cross-section looked like, and then write that cross-section as a function of a perpendicular variable. We had to figure out what the area was based on a variable that ran perpendicular to that area. So we had a bunch of rectangles stacked up in a height. We had to write the area of that rectangle as a function of the height. Then in the hemispherical bowl problem, we had a circular cross-section, and we had to write that as a function of the height. Writing the cross-sectional area as a function of the height. So we're saying volume is the cross-section area multiplied by the height. So the height was usually serving as our delta variable. So the height was our delta variable. I'm going to put delta variable in quotes because this is local verbiage that I use. It's not something that you can search on Dr. YouTube and find out about the delta variable. It's the one that's getting squished. It is perpendicular to the area. We have to write the area in terms of the delta variable. So our job is to write the area as a function of the delta variable. Our job was to write the cross-sectional area as a function of the delta variable. Remember, the cross-sectional area always had to have the same shape, but it could change size. We had to write that size as a function of whatever the delta variable. And this is usually perpendicular to the area. That's what was giving us this whole volume business. The area was perpendicular to the delta variable. We did this in a couple of very contrived ways so far. We've had similar triangles, which is essentially linear functions, and then we've had circles. So we've had circles and similar triangles. Those are the techniques that we've used so far. So far, we've used similar triangles to write our area as a function of the height. And we use the Pythagorean theorem to write our area as a function of the height. And now we're going to do a different one. We're going to find the volume of a solid of revolution. That's our new one today. So let's talk about what a solid of revolution is. What we're going to do to create a solid of revolution is to take a region in the XY plane and rotate it around an axis. So to form a solid of revolution, we rotate a region about an axis. We're going to form a solid of revolution by rotating a region in the XY plane about an axis. For our purposes, the axis is either going to be a horizontal or a vertical line. So our axis is just going to be a horizontal or vertical line. So this is nothing new. We actually have some of these already. If we take a rectangle, so if we take a region that is a rectangle, and we rotate this rectangular region about an axis, our notation for the axis of rotation will be, make like a Gretsch G out of it. If we take a rectangular region and rotate it about this axis of rotation, this will produce a cylinder. Where the axis of rotation is right through the center of the circular face. And here is where we would find our original rectangular region. If we take a triangular region, and rotate it about an axis, that will produce a cone. Our axis of rotation will go through the center of the circle and the tip of the cone. And here is where we will see our original triangular region. Now, we've done these already. The area that we're going to be looking at is still the cross-sectional area. The cross-sectional area always has to be the same shape. So the cross sections that we're looking at are still perpendicular to the axis of rotation, and those are going to be circles. The circular cross-section part comes from the fact that we are rotating a region around an axis. What we want to be able to do, oh, let me do one more. If I take a semicircular region, if we take a semicircular region and rotate it about its diameter, or we put the axis of rotation there at the diameter, we will end up with a sphere. With our axis of rotation going right through the center of our sphere, and we'll be able to see our original semicircular region here in the XY plane. In all these cases, because we're forming our solid by rotating around an axis, we're always creating something circular. We're always going to be working with a circular cross section. So a cylinder has this circular cross section. Our cone has a circular cross section. Our sphere has a circular cross section. So our volume is going to be pi r squared times some height. So we're just looking at our cylinder, our cone, and our sphere. The volume of our slice is going to be the area pi r squared times the height delta variable. Then our job will be to figure out what the radius is as a function of a variable running along the axis of rotation. For a cylinder, r would be a constant function of h. For a cone, r would be a linear function of h. For a sphere, r would be the square root of a quadratic function of h. And we've all done examples of those. what we're going to want to avoid is trying to draw the entire shape. We're going to want to imagine what the shape, be able to come up with the volume for the shape without having to imagine the shape. So we can see all these circular cross sections, and we want to think about what those circular cross sections look like just in the drawing of the region. So this circular cross section here on this cylinder, there's our circular cross section with a radius of r. When I drew my rectangular region, I'm like, oh, dude, you need to draw that bigger. And I was like, oh, nah, it'll be fine. And so now the part that was like, oh, dude, you need to draw that bigger is looking at me. He's like, oh, well, I told you so. I'm like, oh, quiet, you. For our triangular region, here is where we see that piece of that circular cross section. For our sphere, here is where we see that piece of our circular cross section. Now, this is kind of a crazy thing to do for a cylinder, a cone, or a sphere, although it's going to be important to do those because when we introduce some kind of new technique, we have to make sure that it is backwards compatible. We want to make sure that we can play our PS5 games, our PS4 games on our PS5. I guess that's more forward compatible. Anyway, can you play your old games? Or do you have to buy new ones? The reason that we want to do this is that we want to have a stranger cross section that doesn't fit into the category of just cylinder, cone, sphere. Those things happen so often, we don't bother developing the volume of a sphere. We just know it. If we need to know the volume of the sphere, 4/3 pi r cubed, done. That happens enough that we should just remember it. But what if we have a region that is more of what we might call a WTF region? And we form a solid by rotating it about an axis of rotation. Now we could attempt to draw this weird thing. It'd be like some kind of piece of a table leg, I guess, that has like, that's too ornate. I think the table leg analogy clearly demonstrates that this book was written in like the late 80s. Actually, the book was written in the early 90s because they talk about these ornate, weird looking table legs that have been through some work on a lathe. No one builds tables like that anymore. That's how you can tell this book was written in the early 90s by people in their 60s. When it was that who were like bought furniture in the 70s where they had these big, thick, ornate table legs. I'm like, inspiration. And it's like young people today don't know that we used to have these ornate table legs. You know, a table leg, you mean just a cylinder? And then the engineers were like, oh, no, it's a little bit wider at the top. Oh, so it's just a piece of a cone. Because it's just different now. But anyway, I have some fancy table leg. Now we could try to draw this, but I don't want to try to draw it because I can't do it. But it doesn't matter if I can't draw it because it's got a circular cross section. I just need to describe the radius as we go from one side to the other. If I'm rotating about this axis, I'm just going to have radius of a circle. And this is just a stack of circles. We cut this table leg on a lathe. It's just a stack of circles. I just need to find the area of each of those circles and add them up. Because that's how integration works. Integration is multiplication, but one of the factors is continuously variable. So integration is just addition, but messed up addition over a continuum. So there's nowhere to put the plus sign. The volume of this table leg is just going to be pi r squared at each of these circles times delta x. We just need to write it in terms of some sideways variable that's perpendicular to the variable r. Any questions? We can also look at a variation on this theme where the axis is not a boundary of the region. So a variation on this theme is that the axis is not a boundary of the region. I'm going to do this in the simplest case, where we have this rectangular solid or rectangular region. And our axis of rotation is disconnected. It's not a boundary of the region. So we've got this gap between the region and the axis of rotation. So what will happen here, we'll rotate the region around. When we rotate the region around, we're still going to get a solid of revolution, but it's going to have a hole through the center of it. So we'll not just get a cylinder. We'll get a cylinder with a cylindrical hole in it. So here is our original region. And because the axis of rotation is not attached to a boundary of the region, the axis of rotation is not a boundary of a region, we still get this gap. And so we end up with a hole. So our slices are not just full circles. Our slices are circles, but with circular holes in them. We like to describe these as washers. So it's not just a circle. It's a circle with a circular hole in it. So the cross-sectional area is not pi r squared. There's two radiuses that we have to worry about. There's two radii that we have to consider. The outside radius, that's the whole circle, and then the inside radius. That's the part that we're subtracting. So the area of the slice is pi times the outer radius squared minus pi times the inner radius squared. So we have two radiuses, an outer radius and an inner radius. And it just becomes hard to draw. So if we take this washer and look at it where it came from in our picture. Here's the part of the solid, and here is the gap. So this outer circle gets rotated around and the inner circle gets rotated around and then subtracted. Pi outer circle minus pi times the inner radius squared. Our outer radius is measured from the axis of rotation to the outside edge of our slice. And we're subtracting our inner radius, little r, which is the gap. So subtract the radius of the gap. So in this case, we have an axis that is not a boundary of the region. In this case, obviously, we would just find the volume of the outer cylinder, find the volume of the inner cylinder, and then just subtract the two. That's because both shapes are cylinders. Both shapes are cylinders, so of course we would do that. We're not trying to find the volume of the material in this, let's say it's a pipe or something like that. That's not the point of the problem, to find the volume of this thing. The point of the problem is to define a system where we can calculate the volume, even if the outer radius and the inner radius are not just boring ass constants like they are here. I know that we can just subtract the inner circle minus the outer circle, the inner cylinder minus the outer cylinder. Look past the cylinder. It's not about finding the volume of these two cylinders and subtracting. It's about developing a system based on that subtraction that fits with integration, because we're trying to understand the process of integration. This is because the question will always come up. Why don't we just do this? Essentially, the question comes up, why don't we just do the thing that we already know how to do? And the answer is very simple, because we're using the thing that we already know how to do to advance our knowledge to a thing that we don't know how to do. Then, if you really want to fight, the question becomes, well, why do I have to know that? And the answer to that is simple as well. You don't. And it's that simple. I mean, you don't have to know this. And then the question becomes personal, as if I'm supposed to know. Well, why do I have to know this? But I just default to the previous answer. You don't. Then the question becomes seemingly pragmatic, which is just being obstinate. I'm fine with being obstinate. I am obstinate on a regular basis. Well, when am I going to be doing this in my future career? And I don't know, probably never, unless you become a math teacher and happen to get assigned to calculus 2. It has been very applicable in my career, because I have to do this twice a year for the last 20 years. So that's a little bit specific though. So I have a new hopeful answer to when am I going to do this? My hopeful answer is I don't know. No one knows. I want to show you where we've been. So if a problem comes up, you don't have to reinvent the friggin' wheel. It's like a wheel. You don't have to reinvent the wheel just to get over that problem. I want you to know how the wheel was invented so that you can move on and do something more interesting with the wheel, something that nobody right now has even conceived of. So I don't know, and that's the best part. I don't know what we're going to do next. That's the best part. Y'all are probably not old enough to remember when phones used to have full-ass keyboards on them. We used to have physical buttons to make this thing work. And when Apple came along and says, like, well, we're going to get rid of the keyboard and we're just going to touch the screen, everybody was like, oh, I don't know about this. We immediately broke into two camps. Early adopters like, oh, this is exciting. I can't wait to not have to press buttons. And Luddites who were like, oh, I hear this new direction. So, but look where we're all at now. Some people actually still have an iPhone 1 somewhere sitting in their desk, and then the rest of us got rid of our BlackBerry. Just to clarify, I wasn't afraid of buttonless screen tapping. I was just like, oh, you go first. I don't buy software version 1.0. You go first. I am, however, super opposed to touchscreens in cars. That is a hill that I'm willing to die on. And I probably will literally die on that hill because someone will have to look down at their screen and change the seat heater, and then they'll crash into me and we're all dead. So that might literally be a hill that I'm going to die on. But yeah. What are we talking about? Oh, yes. I guess it always just sounds like I'm making excuses for asking you to do arcane shit, but I got to come up with a reason for you to do arcane shit. Because it's cool, man. So what we're going to do is we're going to turn this area of the slice with this weird ass volume into the volume of the slice by multiplying our pi r squared minus pi r squared times delta x. Usually I will write it this way, so I have to write pi less often. And this way, instead of terms, I have factors. But I just have to write r and r in terms of x, which is going to be perpendicular to our radii. This all falls in the category, these discs and washers fall into the category of solids of revolution that I refer to as slicing perpendicular to the axis. Slicing perpendicular to the axis of rotation is when we are doing discs and washers. Discs are pi r squared times delta x. Washers are pi times r squared minus r squared times delta x. The discs is pi r squared. Delta x, there's no hole, so there's only one radius. And washers is pi times r squared minus r squared times delta x. Since I've just created a category called slicing perpendicular to the axis of rotation, you might be thinking, well, what happens if we slice parallel to the axis of rotation? Or maybe you're just like, oh, no, I'm not even going to bring that up. This is like at the end of the day, the teacher hasn't mentioned the word homework. You don't want to be the person that's like, oh, hey, is there homework tonight? You have not announced homework. Because then all the other students will beat you up in the parking lot. But I just created this category called slicing perpendicular to the axis of rotation. This implies the existence of another category called slicing parallel to the axis of rotation. That's just not a thing. I'm just kidding. It totally is a thing. I wouldn't have said anything otherwise. I want to mention this because we have started using searchable language about this particular topic. Dr. YouTube does know about finding volumes of solids in revolution, and they do know about disks and washers. So you can actually just search disks and washers. For slicing parallel to the axis of rotation, we'll talk about this in more detail tomorrow. We're making cylindrical shells. We're going to describe them as cylindrical shells, but secretly, they're just rectangular solids. They're rectangular solids bent into cylinders. This is just another variation on volume. It's cross-sectional area multiplied by the height. It's a different way that we can write the cross-sectional area as a function of a variable in the direction of the height, as a function of a variable perpendicular to the cross-sectional area. That's the structure that we're trying to use. The thinking is the same thinking that we always have for integration. Integration is multiplication, but one of the factors is continuously variable. In this case, continuously variable size, but constant shape. We're just trying to adapt the procedure to weirdo sides. Because we've got the easy ones, cylinder, cone, sphere, we've got those. What happens if our shape is weird? That's going to do it for today. I will see you all on tomorrow, and we'll talk about slicing parallel to the axis of rotation into cylindrical shells, and maybe do some problems. That's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.